Hello everyone. In this video lecture, we are going to study the next shortcut method of finding particular integral in which the right hand side function is product of exponential function and the function of x. And also we are going to solve examples on this method. So let us see this method. Suppose the given differential equation is phi of d of y is equal to f of x. And this right hand side function f of x is the function e raised to x into v, where this e raised to x is exponential function and this v is a function of x and this a is any constant. Then in this case the yp will be 1 upon phi of d e raised to x into v. Now instead of considering v function directly, first we will consider the function u and then we will evaluate the derivatives of e raised to x into u function, different order derivatives of different orders. So let us see that. Consider derivative of e raised to x into u. So apply the product rule of derivative, that will gives us e raised to x d of u plus the derivative of e raised to x, which is a into e raised to x, and u as it is. Now from this we will take e raised to x common to the left hand side and u to the right hand side. So that will give us the expression e raised to x into d plus a of u. So we are going to operate this operator d plus a on u only. So this is first order derivative of e raised to x into u. Similarly, we will evaluate second order derivative. So d square of e raised to x into u is equal to the derivative of e raised to x into u, which is we have evaluated here e raised to x into d of u plus a into e raised to x of u. Now obtain the derivative of these two terms with respect to x like this. So that will gives us, so here we have applied the product rule of derivative. Simplifying this expression, we will be getting the term as e raised to x into d square plus 2ad plus a square of u. This is nothing but the square of d plus a bracket square. So we got d square e raised to x u is equal to e raised to x into d plus a bracket square of u. We are going to operate this operator on u. So this is about first order and second order derivative of e raised to x into u. Now from these two results we will generalize the result as d raised to n of e raised to x into u is equal to e raised to x into d plus a raised to n of u. Now this is for the nth order derivative. Now we will generalize this result to the phi of d function. So that will give us, hence phi of d of e raised to x u is equal to e raised to x into phi of d plus a of u. What we did here, we added all the left hand sides and we added all the right hand side of all the n plus 1 expressions, and from that we got this expression. Now we want to obtain particular integral for ex e raised to x into v, but here we have considered the function e raised to x into u. Now what we are going to do? We are going to make substitution for this term phi of d plus a of u as v. So put v for that term phi of d plus a of u. Now we want to replace the value of u, therefore operate 1 upon phi of d plus a on both the sides. That will give us u as u equal to 1 upon phi of d plus a of v. Now replace the value of this u in the expression 1. So that will give us Phi of d of e raised to ax. See, we have replaced u by this term both on the left hand side as well as on the right hand side. Now, on the right hand side, this phi of d plus a term will get cancelled and we left with e raised to x into v on the right hand side. Left hand side will be as it is. Now, to get the yp, that is 1 upon phi of d of e raised to x. Now we will operate 1 upon phi of d operator on both the sides of this expression. That will give us 1 upon phi of d of left hand side equal to 1 upon phi of d of right hand side, which is e raised to x into v. This phi of d will get cancelled and hence we got our result, which is 1 upon phi of d of e raised to x into v. So which is our required particular integral, which can be evaluated as e raised to ax into 1 upon phi of d plus a of v. So in this way we are going to apply this result. So while solving the example, what we are supposed to do? See, whenever such function is there, then to solve this, we are going to take this e raised to x function to the left hand side of this operator 1 upon phi of d. And while taking this e raised to x to the left hand side of this operator, we have to replace this d by d plus a, where this a is coefficient of x in the exponential function. Okay, so this is very simple thing and very simple rule. Now we are going to solve example on this rule. Let us see the example. First example, solve the differential equation d square minus 2d plus 3 of y is equal to e raised to x into cos x. Solution. Auxiliary equation is d square minus 2d plus 3 is equal to 0. Obtain the roots of this equation, which are 1 plus minus I root 2. So they are two complex roots with alpha equal to 1 and beta equal to root 2. Therefore, complementary function is yc is equal to e raised to x into c1 cos of root 2x plus c2 sin of root 2x, which is the required complementary function. Now we'll go for obtaining particular integral. General formula is yp is equal to 1 upon phi of d of f of x. Replace phi of d by d square minus 2d plus 3 and f of x is, which is the right hand side function, e raised to x into cos x. Now it is of the type e raised to x into v, where our v is cos x, which is a function of x. Hence we will use the current rule. So if we wish to apply that rule, what we are supposed to do? We have to take this e raised to x to the left hand side of this operator, and while doing so, we have to replace this d by d plus the coefficient of x in the exponential function. In this case, here it is 1. So we will replace d by d plus 1. Therefore, the yp will becomes now, see, we have taken e raised to x to the left hand side and we have replaced each of these d by d plus 1. Now simplify this expression further, which gives us yp equal to e raised to x into bracket 1 upon d square plus 2 into cos x. Now we left with the trigonometric function only, because we have to operate this operator only on this trigonometric function, and we know that how we are obtaining yp in case of trigonometric function. We are replacing d square term by minus of coefficient of x in the trigonometric function. Here it is 1, so we'll replace d square by minus 1 square, which is equal to minus 1. Therefore this yp, it will becomes yp equal to e raised to x into 1 upon, we replaced d square by minus 1 plus 2 cos x. Simplifying it, we will be getting yp as e raised to x into cos x, which is our required particular integral. And therefore general solution is given by y is equal to yc plus yp. Now replace yc and yp by their corresponding expressions. That will give us y is equal to e raised to x c1 cos of root 2x plus c2 sin of root 2x plus e raised to x into cos x. So which is the required general solution. So see how simple this method is and how simple this rule is to apply to the given differential equation whose right hand side function is of the form e raised to x into v. For more clarity, let us consider the next example. Solve the differential equation d raised to 4y upon dx raised to 4 minus y is equal to sin x into cos h of x hyperbolic function. Solution. The auxiliary equation is d raised to 4 minus 1 equal to 0. So this can be reduced into the quadratic factors as d square minus 1 into d square plus 1 equal to 0 using the formula a square minus b square is equal to a plus b into a minus b. And therefore equating them to 0 we will be getting roots as plus minus 1 plus minus I. So these are total 4 roots. Therefore, depending upon the nature of these roots, we can write complementary function as for the real roots it is c1 e raised to minus x plus c2 e raised to x plus for the complex root with alpha real part equal to 0 c3 cos x plus c4 sin x. So this is the required complementary function. Now we will go for finding particular integral. General formula is 1 upon phi of d of f of x. Replace phi of d by d raised to 4 minus 1 and f of x by sin x into cos h of x. Now we haven't seen any method in which we have considered the product of trigonometric and the hyperbolic function. But we know the formula for hyperbolic function in terms of exponential function. So we replace this hyperbolic function by its corresponding formula in terms of exponential function, which is e raised to x plus e raised to minus x divided by 2. Now operate these operators separately on these two functions. That will give us 1 by 2 into 1 upon d raised to 4 minus 1 e raised to x into sin x plus 1 upon d raised to 4 minus 1 e raised to minus x into sin x. Now both of these functions they are of the type e raised to x into v. So same rule we will apply to both of these functions. So in the first term we will take e raised to x to the left of this operator and we will shift this d to d plus 1 because here coefficient of x is 1. And in the second term we will take e raised to minus x to the left of this operator and we will shift this d to d minus 1. So that will give us like this. Now expand these brackets. That will give us the expressions like this. So in the first term this 1 will get cancelled with minus 1 and in the second term also this 1 will get cancelled with the minus 1. Therefore the further expression is now in both first term and second term that d raised to 4 we have expressed it as d square into d square plus d cube as d into d square plus 6d square plus 4d. Similarly in the second term. Why we have done this? Because now we left with the trigonometric sine function and we know that whenever trigonometric function is there we always have to express our phi of d in terms of d square except d and the constant term. So therefore we have expressed it like this. Now the coefficient of x in the trigonometric function is 1. Hence we replace d square by minus 1 square which is equal to minus 1. So put this value, replace d square by minus 1 in both the terms. That will give us in the first term 1 upon 1 minus see d square into d square minus 1 into minus 1 is 1 d square minus 4d d square minus 6 plus 4d as it is In same way in the second term. In the first term, minus 4d plus 4d will get cancelled. Similarly, in the second term, plus 4d minus 4d will get cancelled, and that will give us yp equal to 1 by 2 into e raised to x 1 upon 1 minus 6, which is minus 5 into sin x, plus 1 by 2 into e raised to minus x into 1 upon minus 5 into sin x. Now we will take 1 upon minus 5 sin x common. So in bracket we left with e raised to x plus e raised to minus x upon 2, and which is nothing but cos h of x. So this is our required yp. Therefore, general solution is y is equal to yc plus yp. Replacing these yc and yp by their corresponding expressions, the general solution of the given differential equation is y is equal to c1 e raised to minus x plus c2 e raised to x plus c3 cos x plus c4 sin x minus 1 upon 5 into sin x into cos hx. I hope you have understood this method. Thanks for watching this video.